In this video, we're going to look at some ways that we can predict whether or not a given nucleus is likely to be stable. Now, first off, these are trends. None of them are perfect. So sometimes you will encounter a situation where the things we're going to talk about predict that something is stable and it's not, or that something's not going to be stable and it is. That's totally fine. But these are just meant to be some guidelines to help us think about the most common scenarios. So if I'm asking you to predict whether something is stable or unstable, you can assume it's going to kind of fall into fitting these guidelines. I am not going to ask you to memorize exceptions or anything like that. So first thing to be aware of in predicting whether or not a nucleus is likely to be stable is that all nuclei with atomic numbers greater than 83 are unstable. And these tend to be alpha emitters. Let's say they tend to undergo alpha decay. So that is pretty straightforward. If your atomic number is greater than 83, it is almost certainly going to be unstable, and it's probably going to go through alpha decay. So depending on sort of why it's unstable, we can often predict what type of decay is going to be most likely. So in this case, the nucleus is just too big. When your nucleus gets too big, it gets unstable, and alpha decay allows it to get smaller as quickly as possible. The alpha particle is the largest particle that can be ejected from the nucleus, so alpha decay helps it to get more stable as quickly as possible, or in as few reactions as possible. The next thing we can look at is that stable nuclei tend to have a neutron to proton ratio you will often see this abbreviated as N/Z, between about 1 and 1.5 or so. So to expand on this a little bit, N is our number of neutrons, Z is our number of protons. I don't know why it's Z, but it's Z. So using the atomic number and the mass of a given isotope, we can calculate the neutron to proton ratio, and most of the time we find that stable nuclei tend to have neutron to proton ratios in this range. Now, there are stable nuclei outside of this range, and there are unstable nuclei inside of this range, but most of the time it's a pretty good guideline, or at least a pretty good starting point. And depending on whether this ratio is too big or too small, we can predict what type of decay something is likely to undergo. So when our N/Z ratio is less than 1, when our neutron to proton ratio is too small, nuclei tend to undergo either positron emission or electron capture, and you can't really tell which. So if I asked you a question about this to predict what type, I would gladly accept either or both is fine. This down a smidge. When our ratio is too big, is greater than 1.5, nuclei tend to undergo beta decay. So we can predict which of these types is likely to happen based on these different factors. If our nucleus is just straight up too big, atomic number greater than 83 is probably going to be an alpha emitter. If we're outside of this stable 1 to 1.5 range, if our neutron to proton ratio is too small, it's probably going to be positron emission or electron capture. If it's too big, it's probably going to be beta decay. So this is a graph that kind of summarizes all of this in one nice little image. So this red line here is an n over z of 1, so where our number of neutrons and protons are equal. Our 1.5 would therefore be somewhere right about here or so. See if I can get this to be a straight line. Nope, I can't. Cool. Try one more time to make this pretty. Yeah, there we go. So this sort of cone is what we call the band of, or what is sometimes referred to as the band of stability. So this is where stable nuclei tend to lie. Note that all of these blue dots, all of these blue dots in here represent stable nuclei, represent the N to Z ratio of stable nuclei. And you do see that most of them fall within that band. There are a few outside the band down here, and there are a few outside the band up here. But for the most part, our stable nuclei do fall in this 1 to 1.5 range. So these are going to be, for the most part, our stable nuclei in here. We've got Z greater than 83 over here, so this is sort of that too big cutoff. So these guys are all likely to undergo alpha decay over here. And then we've got the positron emission or electron capture sort of region down here, where our N over Z is going to be less than 1. And then we've got the beta decay area up here, where our N over Z is greater than 1.5. So we can see sort of the different regions on this graph are all different neutron to proton ratios, and that can sort of help us predict what is likely to happen for a particular isotope. So let's look at an example and see if we can make a prediction about whether this is going to be stable or unstable, and whether it is likely to undergo, if it's not stable, what type of decay it's likely to undergo. So let's look at uranium-235. So why don't you pause here, take a minute, and try to think about this one on your own. Do you think it's stable or unstable? And if it is unstable, what type of radioactive decay do you expect it to undergo? Okay, so if we think about the symbol for this, or we need its atomic number, this would be uranium-235, which has an atomic number of 92. So in this case, we don't even need to do the neutron to proton ratio thing, because our atomic number is greater than 83. So just based off of that, we can say that this nucleus is likely to be unstable, and it is likely to undergo alpha decay.